Right, section 10.4 is the last section of chapter 4 that we are going over. And this deals with areas and length and polar coordinates. So in order to get started here, we need to recall the area of a sector of a circle. So let's draw a little image of a sector. Kind of just looks like a pie wedge, where theta is the angle measurement here, and then the length of a side is just going to be r. So the formula for the area of a sector of a circle is A is equal to 1/2 r squared times theta. Now let's imagine a larger wedge. This is how we're going to connect it to polar coordinates. So let's say we have some polar curve graphed here. We're going to make little sectors. And up at the top here, this is the terminal angle, so theta is equal to, or the terminal side, theta is equal to B. Over here is where it starts, theta is equal to A. And we'll just call this area 1, area 2, area 3. So we would add up all these areas. So we would say that the area in polar coordinates is A is equal to the integral from theta equals A to theta equals B of 1/2 r squared d theta, where, again, r is a function of theta. So whatever our function is, that's what's going in for r. All right, so our first example, we're just going to set up an integral. So we'll set up an integral for the area enclosed by one loop of the four-leaved rows, which came from r is equal to cosine 2 theta. So if you remember the construction of this from the last section, part of it, and we're just going to go to the portion that's over here. So we would start at this point 1, 0, and then we actually made our way back here. So, and this happened at theta is equal to pi over 4. We were back to the pole. And eventually we made our way over to here too. So looking at this, if we were to travel this way, we would get negative pi over 4. And then up here that would end at pi over 4. So this is going to be the limits of integration. We're kind of sweeping this area as theta goes from negative pi over 4 to pi over 4. So the area is equal to the integral from negative pi over 4 to pi over 4 of 1/2. Our function r is cosine of 2 theta squared d theta. And that's all we were looking at for that problem. All right, our next example, we want to find the area that lies inside these two curves. We'll call R1 is equal to sine theta, and R2 is equal to cosine theta. So we need to know what the graph of this looks like. So we're still practicing from what we did in section 10.3. So let's start with r is equal to sine theta. See what that looks like. So let's make our theta, let's make our r, which is sine theta, and then let's make our ordered pair for the polar plane here. So let's start with 0. Sine of 0 is 0, so we start at the pole, 0, 0. And then let's go to pi over 2. Sine of pi over 2 is 1, so then we're at 1 pi over 2, so it'll be up here. And our radius is increasing, so we start to look like this. Next, let's go to pi. Sine of pi is 0, so we're at 0 pi. We're back at the pole. Then if we did 3 pi over 2, That's going to give us a -1. So this becomes -1 3 pi over 2, which converts into 1 pi over 2. And then we're back up here. So we actually have, even though it doesn't really look like it, this is a circle. Now let's do r is equal to cosine theta. So we would have theta and then r theta. Again, let's start at 0. Cosine of 0 is 1, so we're at 1, 0. So that's going to put us out here. And we'll go to pi over 2. Well, that's 0, so we're at 0 pi over 2. So that takes us back to the pole. And then if we're at pi, that's -1. So this is -1 pi, which converts into 1, 2 pi. So that brings us back out here. So we just have two circles. So this is r is equal to sine theta. This is r is equal to cosine theta. So we need to find where these two curves intersect. And that's where sine theta is going to equal cosine theta. And that happens when theta is equal to pi over 4, because we're looking in the first quadrant here. So remember, it comes back to pi over 4, which would be right here. Now they also intersect at the pole. But if you notice, what got us to the pole was 0 pi, and then down here 0 pi over 2. So they have different values that took them to the pole. So we're not going to use those. We're going to use the pi over 4. And then I'm actually going to draw that dotted line here when theta is equal to pi over 4. So as I'm going from 0 to pi over 4, so that's going to be our area. As I go, we'll say as theta goes from 0 to pi over 4, we're sweeping out this area right here, so just below. But there's some symmetry, so we're going to exploit that symmetry. So we're going to write this as the area is going to go going to be the integral from 0 to pi over 4 of 1/2 sine theta squared, because that's the lower part of the circle. See how that's in red there? So that's part of the curve r equals sine theta. But because that's only the lower half of that intersection point, or the intersecting area, we're going to double that. So this will be d theta. But that's only half of the area. So the area we want is double this value that's right here. So we're just going to say that's 2 times the integral from 0 to pi over 4 of 1/2 sine theta squared d theta. So exploit the symmetry. And then we could just go through and evaluate that integral. But right now, the most important part is just being able to set that up. All right, so let's go through a couple more examples before we focus on arc length. All right, again, even though I'm going to tell you to find the area, let's just set up the integral. Afterwards, you will be able to figure out the integral yourself. And what I told class on Tuesday is you can go to, I think it was by Symbolab. It's a definite integral calculator. I forget if it's in this section, some problems maybe in this section, or the last section will have you do that. It tells you to use your calculator to find the integral, and that's where you can use this. But if it is possible to evaluate the integral by hand, then you definitely want to do that. All right, so for this next example, let's find the area, or at least set up the integral to find the area. of the region lying inside r equals 1 minus sine theta, and outside r equals 1. Well, in section 10.3, we looked at something like this. I think it was 2 times the quantity 1 minus sine theta, and that graphed a cardioid. So anytime we see something like this, it's going to graph something very similar, so we don't have to go through the process of making a table again. So what the cardioid is going to look like is we're going to go out to 1 on either side, and sine is always going to be like a heart shape that's normal, like a normal rotation. When it's cosine, it's going to be rotated or sideways, so rotated 90 degrees. So for the cardioid here, for r equals 1 minus sine theta, we're going to double what we go down compared to right here. So this is going out 1, and then we're going down to -2 here. So we start here, and it looks like this, to here, and then down. And then r equals 1 is just a circle of radius 1. Not going to look much like a circle, but close enough. So we want to find the area of the region lying inside the cardioid, but outside of the circle. So inside the cardioid, but outside of the circle is what's here in blue. So we want to still find out what theta measure these angles or these curves intersect. So we're going to set 1 minus sine theta equal to 1. So I'm going to subtract 1 from each side, so we'll get negative sine theta is equal to 0, and then sine theta is equal to 0. So that means sine theta is equal to 0 when theta is equal to 0, pi, 2 pi, and so on. But if you think about what took us to these points right here and here, this would be when theta is 2 pi, because we're just sweeping around, and this is pi. So our area is going to be the integral from pi to 2 pi of 1/2, and we're using the cardioid right here, which would become 1 minus sine theta squared d theta. But if we left it at this, this is going to find the entire area inside the cardioid. We need to subtract what would be up here. So everything that I have listed is finding all of this in purple, but we need to subtract this top part. So we need to subtract the integral from pi to 2 pi of the part of the circle that's right here, which is 1/2 of 1 squared d theta. This would be the area inside the circle. And I shaded a little bit too much because all of this is just underneath the polar axis, so we cannot go above that. So let me adjust that part right there. So this would be the area, because we're just going from pi to 2 pi, so we're staying below the x-axis. So area, or the polar axis, below the polar axis. And then this would be the area inside the circle below the polar axis. All right, we'll try one more example of finding the area with respect to some curves here. So let's go ahead, set up the integral that will help us find the area inside r is equal to 1 plus cosine theta, and outside r equals 3 cosine theta. So let's go ahead and get this graphed. All right, so we just did r equals 1 minus sine theta. So if we did 1 plus cosine theta, and again, you can make the table off to the side to do this, but this is going to be a sideways heart. So it's going to look like this, and then we'll double. So it'll look like this. So this is r is equal to 1 plus cosine theta. And then r is equal to 3 cosine theta. That's just going to be a circle. Remember, a couple examples ago, we just did r equals cosine theta. So we're going to take, that means we have a radius of 3, so we're going to go out here, and then we have a circle that looks like this. That's taking it out to 3. So we want to find the area inside the cardioid and outside r is equal to 3 cosine theta. So that's this area right here in red. But again, we need to find where these curves intersect. So let's set 1 plus cosine theta equal to 3 cosine theta. And we'll subtract cosine theta from each side, so we get 1 equals 2 cosine theta. So cosine theta is going to equal 1/2. And cosine theta is going to equal 1/2 when theta is pi over 3. So it's at 60 degrees. So if we're looking, that means we're kind of going up this way. So the circle kind of comes back right here, and then this comes down at theta is equal to pi over 3 radians. Now we also need to consider they intersect at the pole. So if we took 1 plus cosine theta, set that equal to 0, we would get cosine theta is equal to -1, and that happens when theta is equal to pi. And then 3 cosine theta is equal to 0 when cosine theta is equal to 0, and that happens when theta is equal to pi over 2. So again, they happen at different values of theta, but we are going to need them here. So if we set up the area to equal, I'm going to do this in a different color, because right now if we start at pi over 3, we also have this little bit of area that's right here. So the first integral, and again I'm going to exploit the symmetry here, we're going to have 2 times the integral from pi over 3 to pi of 1/2. So if I'm looking at the cardioid, we're going from pi over 3 all the way over to pi. So that's what's going to take what we have in blue right here from their point of intersection. And we're doubling it because we'll have the same area down here. So that's why the 2 is there. So then we get the 1 plus cosine theta squared d theta. But then we need to subtract this little part that's right here. And we would also have to subtract it on the other side because there's some symmetry. So we'd say -2 times the integral. So we would just go from pi over 3 to pi over 2. But the function we're going to use here is the 3 cosine theta squared d theta. Because if you think, if we're on the circle from pi over 3 to pi over 2, that's what's going to follow this green back to the pole here. So that would be our integral. And what's really helpful is if you do make the table off to the side of plotting these, you'll be able to see these theta measures kind of show up a little better. All right, so now let's take a look at arc length. We have a little bit more of a straightforward formula. So again, let's go back to our famous parametric equations here, where x is equal to r cosine theta, which again is the same as f of theta cosine theta, because r is equal to f of theta. And then y is going to equal r sine theta, which is f of theta sine theta. So now arc length is going to be the integral from theta equals a to theta equals b of the square root of dx over d theta squared plus dy over d theta squared times d theta. But we need to get this in terms of r and theta. So let's examine dx over d theta squared plus dy over d theta squared and simplify it. So without boring you with the details or just kind of going through this, we could jump straight to the final simplified version of this. So it is the integral from theta equals a to theta equals b of the square root of r squared plus dr over d theta squared d theta. So that's going to be our formula for arc length. So let's go through an example. So we want to find the length of r equals 3 sine theta as theta is in between 0 to pi over 3. So our solution, just go back to the formula, we're going to have L is going to equal the integral from theta equals 0 to theta equals pi over 3 of the square root of r squared, so that's 3 sine theta squared, plus the derivative, so dr over d theta is going to become 3 cosine theta. So that's what's going to go here. So we'll go ahead and square everything. So this becomes 9 sine square theta plus 9 cosine square theta. And just as we saw with an example in section 10.3, we could factor out a 9, and then sine square theta plus cosine square theta is 1. So we get the integral from 0 to pi over 3 of the square root of 9, which is 3 d theta. So then we're going to get 3 theta from 0 to pi over 3. So that'll just give us 3 times pi over 3, which is pi minus 0. So we get pi.